recapitulate what we have done. Uh, we started our discussion with that pure metals or materials which are good conductors at room temperature, they do not show superconductivity at low temperatures, whereas materials which do not have that good conductivity at room temperature, they show superconductivity. इससे भी पहले we discussed what we discussed कि what is required for to reduce conductivity of to reduce resistivity of any material, or on what factors resistivity of a material depend. And we said that resistivity mainly depends on temperature, and it also depends on purity of that material. So both the things were tried by Kamerling Owens, and he said that if I reduce temperature to very low temperature, and I make a material very pure, what should be its resistivity, or what should be value of resistivity at very low temperature? So in search of answer to this question, he tried mercury, and he observed that when mercury, which is a metal and which can be purified by repeated distillation processes, so he purified this material to the purest form, and then he reduced temperature of this by using liquid helium. Okay, that story we discussed. तो liquid helium का boiling temperature 4.2 था, तो when it is in liquid state, तो temperature we can attain temperatures, very low temperatures. Okay, so helium was used to cool mercury, and it was observed that at 4.2 Kelvin, when temperature was reduced gradually, and at 4.2 temperature, sudden change in resistivity. There was gradual decrease in resistivity, but sharp decrease in resistivity, abrupt change in resistivity, and resistivity suddenly it falls to zero. Or then this is what this is called. This is called transition in the state from normal state to the superconducting state. And the temperature where this transition happens is called critical temperature, and it is different for different materials. All these things we have discussed. So now we know what superconductor is: a material whose resistivity abruptly changes to zero at low temperatures. Okay, so that means we have a material through which we can send any amount of current. Resistivity is zero, no joules heating, and it will not offer any resistance, so no continuous source of EMF is required to keep that current in the running in the circuit or in the conductor. So there was a temptation: how much current we can send through this superconductor. Okay, so then there is again what? There is a restriction: how much current can be sent through a superconductor. You cannot send any, or you cannot send any current through the superconductor, because the current which will flow through the superconductor, it will produce magnetic field, and magnetic properties were also studied by these are the things which we have discussed. So we were discussing this, that effect of magnetic field on a superconductor. तो हमने कहा कि superconductor, if it is not only temperature, by increasing which we can destroy this state of superconductivity. If we increase temperature of the given material above its critical temperature, then a transition happens from superconducting state to the normal state. With this, there is another factor which can affect superconducting state, or which can destroy this superconducting state of the material, and that is magnetic field. So highest magnetic field which is required to destroy superconductivity of any given material at a given temperature is called critical temperature for that temperature, or sorry, critical magnetic field at that temperature. Okay, if material is at maintained at temperature Tc, that is critical temperature of that material, no field is required to destroy its superconductivity. Zero field is, you can say, required. But lower and lower is the temperature of the material below its critical temperature, more and more magnetic field is required to destroy superconductivity of that material. Or more magnetic field it can withstand. We can apply more, by applying more magnetic field, it will withstand. That means its superconducting state will not be destroyed, or it will not undergo transition from superconducting state to the normal state. So that is explained by this. This is very important relation. This is Hc, which is critical. You can see critical magnetic field, and at different temperatures, this is different for a given material. We have a given material, well-defined Tc for that material, and these temperatures are less than Tc, means we are maintaining that material below its critical temperature, means it is in superconducting state. Even then, without varying temperature, we can do what? We can destroy its superconductivity by applying magnetic field according to T, and we see that. So we can see it here, that this is what, this is temperature which is less than Tc, and magnetic field required to destroy its superconductivities. This is that value. If it is maintained at lower temperature, it is lower than this temperature, higher magnetic field is required to destroy superconductivity. So lower and lower is the temperature, higher and higher is the magnetic field required. So it is given by this relation which we discussed earlier. This is numerical point of view, so it is important. This is the maximum magnetic field. This is required at 0 Kelvin. When material is at 0 Kelvin, then how much magnetic field is required to destroy its superconductivity. And these are the materials, some examples where critical magnetic field at 0 Kelvin means maximum magnetic field to destroy their superconductivity. It is given here. Then we said that the most important effect was given by Meissner. Meissner ने आपको ये बताया कि what happened when we apply magnetic field on any material or superconducting material. When material is in a superconducting state, then till now it was known that rho zero is the only criteria, or is the only condition which decides superconducting state of any material. If rho is zero, resistivity is zero, that means material is in superconducting state. But when we have this, or in light of Meissner's effect, we now understand it is not only rho zero which decides superconducting state of any material. With this, it is what? It should obey Meissner's effect, means it should expel all the magnetic field from its interior, and magnetic flux should also be zero. Or it should go to a diamagnetic, it becomes perfectly diamagnetic material. So there are two properties, electrical properties, that resistivity should be zero. Another independent property, rho zero does not lead to B zero. There is another property, and that property is what? It is magnetic flux through that material is also zero, or we say that susceptibility of that material becomes -1. So a material whose susceptibility is -1, or we can say it is perfectly diamagnetic, or which expels all the magnetic lines from its interior with rho zero, is superconducting state, or material is then said to be in superconducting state. Okay, so we know that if we have a material which is at normal temperature, or you can say at room temperature, it is at room temperature, and we apply magnetic field on this, resistivity is not zero, it is normal state, and we apply magnetic field on it, we see that some magnetic lines, this is magnetic flux is there, B is non-zero. But if it undergoes transition or we lower its temperature and there is transition at T equals to Tc, as soon as this temperature is reached, that is Tc, it will expel all these magnetic lines from its interior. And then for these temperatures which are less than Tc, resistivity of material is zero, but with this magnetic flux density is also zero. So these two properties, that is rho zero and B zero, which are independent of each other, they decides whether material is in superconducting state or it is in normal state. If rho is zero but B is not zero, magnetic flux is linked with the material, then that state is not superconducting state. It is a new state. Okay, and this is the criteria to decide whether it is that state or not. We know that magnetic flux through any material at normal temperature or any temperature, it is what it is, magnetic field applied from outside, okay, that is H, plus magnetization vector M. This relation you are familiar with, you know this relation. And in case magnetic flux, this is Meissner's effect is what, when B becomes zero, then we have what, mu naught times H is equals to minus mu naught times M. Or you can say that this is equals to this, or magnetic field applied is balanced by magnetization due to its magnetic dipole. They get aligned in the opposite direction, opposite to the applied magnetic field. And then this ratio of M magnetization per unit applied magnetic field, which is called susceptibility, is -1. So B0 means what? B0 flux is 0. That means it is expelling all the magnetic lines through it. And how it happens when applied magnetic field is opposed by the dipoles, magnetic dipoles, or their dipole moment is in such a way that it opposes the external field. So magnetization per unit magnetic field, it is then what they are, or we can say -1, or they are equal. So resistive is this susceptibility becomes -1, and this state is what, or material having this magnetic property is called perfect diamagnetic material. So material becomes perfect diamagnetic under T less than Tc, okay, and resistivity of the material goes to zero. This was given by Meissner. He said that this is the additional property which should be there in material for it to be in superconducting state. Okay. So now we understand when T is less than Tc and applied magnetic field should be less than, only that will be expelled. Okay, magnetic flux will be zero if applied magnetic field is less than the critical magnetic field. If you apply a magnetic field, then it starts penetrating. Then it goes from normal state, it goes to normal state. Okay, so magnetic flux lines are expelled up to certain strength of magnetic field, and when we increase magnetic field beyond that, then magnetic lines, they start penetrating the material, or the superconducting material, and superconductivity is destroyed. As soon as B starts becoming non-zero, that means it goes off. This superconducting state is not there. Okay, deciding property, you can see that this is what this is. Susceptibility is -1. It is perfect diamagnetic material. रिवर्सिबल है. एज यू इंक्रीज टेम्परेचर अबव TC, ठीक है, लाइन्स दे स्टार्ट पेनिट्रेटिंग, एंड एज टेम्परेचर इज बिलो TC, then it expels all the magnetic lines through it. And these are the two conditions for a material to be a superconductor or in superconducting state. That is, resistivity should be zero and magnetic induction or magnetic flux should be zero when in uniform magnetic field, or these two states are achieved when T is less than TC and H is less than HC. Okay, and simultaneous existence of these conditions, they decide whether material is, or then material is what it is in superconducting state. So then there is very interesting phenomena which result because of this Meissner's effect, and that is levitation. Levitation क्या होता है कि जब we have a superconducting material, this is my material is in superconducting state, and if I place magnet over this superconductor, this is at temperature less than TC, and magnetic field applied is also less than TC, sorry, HC. It is in superconducting state. That means जो भी यहाँ पे magnetic field आएगा, it will expel all those magnetic lines. So it will repel this magnet over it, and it starts levitating. It starts floating. It starts floating over this superconductor. So I have tried, एक मैंने यहाँ link आपके लिए बनाया था. Let us see whether it is working or not. To show you, I think I should. To show you video on how it levitates. Why it is not working? Okay. Earlier it was working. Now it started. We'll see in this video that there is there's some YouTube video. I don't know why it is not going there. Okay. Chaliye, I'll show it to you some other day because I don't know why it is not working. Okay, so this is applications of Meissner's effect, as it expels all the magnetic field, because we say that if material is in superconducting state, that means it is perfectly diamagnetic material, and perfect diamagnetic material means that it will repel the magnet, or it will expel all the magnetic field lines through it. And there is a the application state, you can see this is called maglev train. The maglev train is based on what? It is based on this Meissner's effect, levitation. It levitates over the track. So that means there is less resistance between the track and the train. So speed of this is very high. You can search this on net, and you can collect more information about this. But as from this point of view, superconductive point of view, we can discuss only this much, that this works on this Meissner's effect. So here you can see this is one animation. This is what this is, magnetic levitation. You can see this is material, magnetic material maintained at temperature less than its critical temperature. It is in superconducting state with rho zero. It is perfectly diamagnetic. Susceptibility is -1, means H is equals to -m, means external magnetic field is countered by magnetization developed inside this. So it is expelling all the magnetic lines through it. And you can see that this is expelling magnetic lines produced by, or magnetic field produced by, this magnet which is placed over this superconductor. So it is levitating, it is floating in air above this superconducting material. And why it happens? This happens due to surface currents. Okay, this is what it is in normal state, but it goes to this material, this conductor goes from its normal state to the superconducting state. So then you see that these are the surface currents. And these surface currents, they induce magnetic field, which compensate the outside magnetic field. So there is screening, shielding of this material. So this is, we'll see this in more detail. Then we have, these are the materials which can be made superconductors, or which show superconductivity at low temperatures. So as I said, that good conductors like gold, silver, copper, they are good conductors. They are best conductors, which we use these conductors for, where silver paste is used to have electrical contacts in electronic circuits. Copper wire, you all understand. Gold is also used, but it is costly, so it is not used that much. So they are good conductors, but they do not show superconductivity. Okay, and similar is here. Ferromagnetic materials are not superconducting. They do not show superconductivity. Niobium has highest, अगर pure elements की बात करें, तो pure elements में highest critical temperature is for niobium. It is the highest temperature, critical temperature, where superconductivity is shown by pure elements of periodic table. So it is 9.2 Kelvin. Okay, and बाकी तो you understand कि we have achieved 1.135 and above temperatures. So now before this, let me, because now as I said that Meissner's, now we are interested in distinguishing between pure conductor and superconductor. How we decide whether material is in superconducting state, or it is simply a pure conductor. So for that we have experiments to do. Let us do experiment number 1. I have a material. This is my material, which is at temperature above, or you can say it is at high temperature, room temperature. This is at room temperature. Okay, we cool this material, we do cooling, and we see that resistivity here, resistivity was non-zero. Resistivity is not zero because it is at finite temperature, or it is at room temperature. And if we cool it, by cooling we can reduce resistivity of this material to very low value, or you can say zero. It is at T when it is very low. Now if we apply magnetic field from outside on this material whose resistivity is zero, because we want to say that we are interested in proving that rho zero and B zero, these are independent properties of superconducting state. Means rho zero, it does not lead to B zero. Okay, and for that, let us take, let me say that I have a material which is a perfect conductor. Means resistivity of that is zero. Okay, and resistivity zero will lead to what? What will be the magnetic property due to rho zero? So for that we have Maxwell's third equation, that curl of E is equals to negative of d by dt of B, and electric field, or I can say current density J, is conductivity times electric field. This is Ohm's law, or I can write that E is equal to rho times J. For a perfect conductor, we are doing it for, we are saying that we have a perfect conductor. So resistivity of perfect conductor is zero. So electric field from this relation is also zero. As this is zero, then d by dt of B is zero, and this means that B is constant. Okay, so rho zero leads to what? It leads to B constant. Magnetic flux should remain constant. So now to distinguish between what? On the basis of this, we can distinguish between perfect conductor and a superconductor, because electrical property दोनों का क्या होगा? Resistivity zero. Perfect conductor means what? Whose resistivity is zero. Superconductor is what? It is again whose resistivity is zero. But Meissner's effect is the effect which plays crucial role here to distinguish between a perfect and then what is the difference? Question is, then what is the difference? Why it is called a new state? Superconducting state is a new state. It is like perfect conductor. And for perfect conductor, we see here that rho zero should need to be constant and magnetic flux should remain constant. But it is not this normal state. It is what? It is a new state. And to prove that it is a new state, let us do this experiment. We have experiment number 1, where we say that we have a material which is at room temperature, resistivity is non-zero. We cool it to very low temperature, where its resistivity vanishes, it becomes zero. Then if we apply magnetic field on this material, then we see that magnetic flux density is what it is, zero through this. Rho is zero here. B is also zero, but this is not a superconducting state. Why B is zero here? It is due to this B constant. As B is zero here, no change in B. That it is B is zero even when we apply magnetic field. So this is what, this is a perfect conductor. This is not a superconductor. Okay, let us do experiment number 2. Let us take superconducting material. This is my superconductor. It is at temperature above critical temperature. Resistivity of this material is non-zero because it is above Tc, temperature is above Tc. We cool this till T becomes less than Tc. Now resistivity becomes zero. And now let us apply magnetic field. Is this transition, that transition where we say that it is in superconducting state or not? Let us apply magnetic field, and again you see what you see, magnetic field is zero, rho is zero, magnetic flux is zero. We say that this is superconducting material, but this is a perfect conductor. Then what is the difference? Both are the same experiments, no difference. Then why we are saying that this is a superconductor and this is a perfect conductor? So we have to do more experiments. Let us do experiment number 3. Let us take this again. We have this, you can call it as a sample 1. This is sample 1. And this is my another material, which is my sample 2. Let me take sample 1 again. This is my sample 1. It is at, you can say, room temperature. Resistivity is non-zero. Let us apply magnetic field here on this. We see what? Magnetic lines, magnetic flux density is not zero. If I cool this, now resistivity becomes zero. We have cooled it to very low temperature where it loses its resistivity, but magnetic flux lines are still there. They are penetrating through this. So rho is zero, but this transition is not that transition where material goes from normal state to superconducting state. The state is not superconducting state because rho is zero, but B is not zero. It is not expelling this magnetic field on cooling. Whereas if I take my sample 2, then this is at temperature more than Tc. Magnetic field is applied. Magnetic flux density is non-zero through this material because it is in normal state. Resistivity is also non-zero. Magnetic flux is also non-zero. But when I cool this, what you see is resistivity 0 and B is also 0. So this means what? B is not constant. B is not constant. Here B is finite and B becomes 0. But in this case, you see this is due to what? Rho 0 is leading to what? Rho 0 is leading to B, you can say, constant here. In these two experiments, it is due to this theory that when rho is 0, that leads to B constant because B is 0, B remains 0, B remains same, it remains constant. Whether magnetic field is applied initially or not, in both these experiments, experiment number 1 and 3, we can see that B remains same, constant. So this is a perfect conductor. Whereas in experiment number 2 and experiment number 4, we can see that magnetic flux B becomes 0 due to transition of material from normal state to the superconducting state. Okay, so this is showing Meissner's effect. ये दोनों कौन से effect हैं? These are Meissner's effects. Due to Meissner's effect, it is expelling the magnetic fields from its interior. So this is how we can distinguish between a perfect conductor and a superconductor. Okay, and this is that these are two independent properties. Rho 0 leads to B constant, but it never leads to B 0. So that means due to this, B is not 0. So this is independent property. B 0 or this is independent of rho 0. Whereas in case of perfect conductors, जो magnetic lines penetrate नहीं कर रही हैं perfect conductor को भी in case of experiment, that is due to B constant. So this is how we can distinguish between two states, normal state and superconducting state. So you can see above this, these are normal states. This is not superconducting state, whereas these are superconducting states. They are different from normal state. Okay, just to justify that rho 0 and B 0 are independent, we have done these 4 experiments, and superconducting state is different from normal state. And Meissner's effect is not that which we see in case of perfect conductor. Okay, that is not Meissner's effect. That is simply what? That is rho 0 is leading to B constant. Meissner effect is not that rho 0 की वजह से B 0. Okay, so then we have type 1, type 2 superconductors, but उससे भी पहले there is a theory why this what is the origin of this superconductivity. There were two physicists, Bardeen, Cooper, and Scheffer, and they tried to explain, or they explained superconducting state of a material. What happens at very low temperature? How resistivity goes to 0? This was not attempted by anyone. People were just running after discovering new materials having more and more critical temperature and all other things. But nobody was explaining, or there was no attempt, or people were attempting, but successfully these three people, they explained what is the reason for superconductivity. So it is in normal conductors, at normal state, electron repulsion, we know, we understand it is electrostatic electric repulsion between two similar charges. But at low temperature, it was predicted that Cooper pairs are formed. What are these Cooper pairs? I'll explain this to you in a minute, because this animation will run this animation. You'll see what it will show you how Cooper pairs are formed. So we say at low temperature, there is electron attraction via phonon. Phonon is what? Phonon is lattice vibration, quantum of lattice vibration. जैसे लाइट इलेक्ट्रोमैग्नेटिक रेडिएशन का पैकेट ऑफ एनर्जी is called photon. Similarly, phonon is lattice vibrational energy, and quanta of lattice vibrational energy is called phonon. So phonon होने की वजह से, लैटिस में वाइब्रेशन होने की वजह से, electron attracts another electron, and this makes a Cooper pair. There are two electrons, and there is what? There is attractive force between two due to lattice vibration, due to phonon, and this makes a Cooper pair. Now, electron is not moving individually as in case it does in case of pure conductors or in case of normal conductors, but Cooper, now it is in the form of a Cooper pair. Electron at high temperature is a fermion having half integral spin, whereas this Cooper pair is a new, you can say, type of charge carrier where we have two electrons bound together, and this is having integral spin. These are integral spin particles now, and these are called bosons. So there is different statistics to understand bosons and fermions. ठीक है, bosons वो particles हैं जिनका spin integral spin है, और half integral spin particles को हम fermions कहते हैं. Fermions के लिए we have Pauli exclusion principle. No more than two electrons can have all the same quantum numbers or quantum states. Bosons, where there is no restriction of this Pauli exclusion principle. All the bosons, they can occupy the same energy state. Okay, so these are some basics which you should know to see how they explain superconductivity. So I said there's one key that at low temperature, lattice vibrations कम हो जाती हैं, ठीक है, and here you can see these red dots or red circles with black dot inside that red. This is representing what? Ions, or you can say atoms in the lattice. These are latticeites. These are latticeites, and this blue dot is what it is? Moving electron. Okay, when this electron, because lattice vibrations cease कर गई हैं, temperature is very low, it is less than Tc, तो thermal energy बहुत कम है, kT, thermal energy is very low or negligible here, so they do not vibrate, thermal vibrations नहीं है. और यहाँ पे जब इलेक्ट्रॉन एंटर कर रहा है इस लैटिस में, you can see that there is distortion, there is lattice is distorted. यहाँ पे ये red dot, it was here, and there is what it is, this you can say, this is the original position, say there is distortion in the lattice. These are positive ions, and electron is moving, and it is creating what? It is creating phonon, this vibration in the lattice. Okay, as it moves ahead, and or you can say that positive field is created here due to these two positive ions. They are now closer to each other than at normal or when there was no electron. Okay, here in this region, there is more distance between two positive ions, whereas here it has reduced. So positive region is created due to this electron presence of electron, or due to this vibration, due to creation of phonon. When this electron moves ahead from here, this positive region attracts another electron. So there is what directly electron is not attracting electron, but electron is attracting another electron due to this positive field which is created. Means via this phonon, this vibration, this lattice deformation. This lattice deformation created by first electron is attracting another electron towards that region. And this makes Cooper pair. This is what this is called, Cooper pair. You can see, this is how electron is moving, and this is how lattice vibration is created. तो जहां जहां पे इलेक्ट्रॉन जा रहा है, I can play it again for you. Electron पे you can see here positive region is created and another electron will be attracted towards that positive region. Here now this is what this is, positive region is created. So यहाँ जो electron होगा it will be attracted towards this positive region. So the lattice deformation creates a region of relative positive charge which can attract another electron. Okay, so this attraction makes Cooper pair, and distance होगा during one phonon oscillation. You can see here one phonon oscillation. It gets deformed and then it goes back to its original position. Okay, these are like harmonic oscillators, elastic springs, like elastic. They can be modeled like that. So during this one phonon oscillation, electron can cover a distance of 10 raised to the power 4 angstrom inside this lattice. The second electron will be attracted without experiencing the repulsive electrostatic attractive force or electrostatic force. Okay, so एक phonon, or you can say एक electron, it will create a phonon. And it will, during this oscillation, it will cover a distance of 10 raised to the power 4 angstrom. And within this distance, say less distance, but there should be what? There should be phonon, you can say electron attraction via phonon. इससे ज़्यादा अगर डिस्टेंस पे चला जाता है इलेक्ट्रॉन, तो व्हाट विल हैपन, वो जो फोनॉन क्रिएट हुआ था, जो लेटेस्ट वाइब्रेशन क्रिएट हुआ था, जो पॉजिटिव फील्ड क्रिएट हुआ था, दैट विल बी न्यूट्रलाइज्ड अगेन. Then it will not be able to attract the other electron or the second electron. So this was proposed, this was given, this theory, and you can see that one of these scientists, it is Cooper is also there. So after Cooper, this pair was, this electron attraction was explained by him, electron attraction via phonon. This is model for, okay, so this is phonon, that lattice vibration, and due to that lattice vibration there is electron attraction, and this is the coherence length as we discussed. तो कहाँ तक वो इलेक्ट्रॉन को अट्रैक्ट करेगा, जब तक फोनॉन वाइब्रेशन विल नॉट डाई. इफ फोनॉन वाइब्रेशन या फोनॉन जो क्रिएट हुआ था वो डाई कर जाता है, मतलब लेटिस वाइब्रेशन जो क्रिएट हुआ था वो डाई कर जाता है, देन इफ डिस्टेंस बिटवीन टू इज मोर देन दैट, तो देन उससे ज्यादा डिस्टेंस अगर कवर कर लेता है इलेक्ट्रॉन, या द डिस्टेंस कवर्ड बाय इलेक्ट्रॉन इज मोर देन द, और दैट यू कैन से कोहेरेंस लेंथ, or distance between two is more than the coherence length, so there will be no electron and electron interaction via phonon. And this binding, we can say that when temperature is less than Tc, so उनके बीच में बाइंडिंग है, इलेक्ट्रॉन पेयर, कूपर पेयर बन रहा है, बाइंडिंग एनर्जी ऑफ कूपर पेयर, एनर्जी प्रोवाइडेड बाय द ऑसिलेटिंग, you can say the energy is provided by the oscillating atoms, and in superconductor electron pairs form Cooper pairs. At temperature Tc, pairing is complete. All the electrons, they show this pairing at low temperature, and it will be destroyed, है ना, phonon vibrations और ये destroy होगा at high temperature. So there will be what, there will be scattering of electrons. Scattering of electrons will be minimum when T is less than Tc, because it will move as a cohesive unit, and it will be in, it is a boson, and it will occupy the same energy state. All they will be in the same energy state. So to break all those Cooper pairs, big energy is required, which is when T is greater than Tc, that energy is uh, that energy it gains, and then again they become fermions, and they occupy different energy states. So you can see here, this is for single electron, which is in case of perfect conductors. When we have a perfect conductor, or we have any conductor, we have room temperature, normal state, material is in its normal state, then electrons, they move individually. There is no electron attraction, or phonon, or you can say Cooper pairs are not formed, and they are not bosons, they are fermions. So electrons are fermions, and they obey Pauli exclusion principle. You can see here, at every energy state we have only two electrons with opposite spins, and this is Fermi drag distribution function for fermions. So then there is what? There is repulsive force. So single electrons, they move now. Single electron is moving, and they get scattered, and they show what? Finite conductivity, or resistivity is also there. So then we have what? We have Cooper pairs, and these Cooper pairs are different. Their nature is different. They are not fermions like single electron. They are bosons, and they do not obey Pauli exclusion principle. Can at low temperature they condense to low, उनका temperature सब, sorry, low temperature सबका energy level जो है वो lowest energy level पे, these are all Cooper pairs having same energy, occupied same energy state. They occupy the same energy state, and they move now as a cohesive unit. No scattering, है ना? और ब्रेक करने के लिए टेम्परेचर रिक्वायर्ड इज Tc. It is at very low temperature, less than Tc. They are in this state, they are bosons, and they are in this state, single state. But as temperature becomes above this Tc, then वो energy is enough to break these Cooper pairs, और ये फिर they will have this type of distribution. So Cooper pairs are not scattered, hence they have infinite conductivity or zero resistivity, and coupled motion up to certain distance, as we say, which is called coherent length. और से ज़्यादा distance होगा तो coupled motion नहीं हो पाएगा. And these three people, they are Bard and Cooper. They got Nobel Prize for explaining superconductivity, or their theory is called BCS theory. B for Bardeen, C for Cooper, and S for Schaeffer. BCS theory. And this is their paper, Theory of Superconductivity. They explained superconductivity, physical review. They published it in 1957, and they got jointly, they were given this Nobel Prize in 1972. Okay, then we have London equations. The more development in the field of superconductivity was made. This is all what we have done, creation of how Cooper pairs are created, and how this is all about that. So we have London equations, and there were two brothers, London brothers. They explained superconductivity. They explained Meissner's effect, how theoretically they explained what happens. Experimentally, Meissner showed that expulsion of magnetic field is another property of superconducting state. It expels all the magnetic lines through it. And theoretically, it was explained by London brothers. They explained what happens in case of superconductors and how they expel all the magnetic field through it. And they also defined a new term that is called penetration depth. ऐसा ही हमने skin depth, penetration depth we discussed in case when we said that electromagnetic wave is going through perfect conductor or through conducting medium. So in the same, you'll see the same type of expression here as well. So that will explain how, what is Meissner's effect exactly. It will explain that. So this is थोड़ा सा derivation में takes time because इसलिए we'll do that next time. And then we have also type 1, type 2 superconductors. We'll explain, we'll see this as well. Then more some small phenomena. We'll see effect of current as well. Coherence length. Okay. So not more than one more lecture is required. है ना? तो एक lecture के बाद this will be over. So we have tomorrow's lecture, Thursday, and then this will complete this superconductivity. And then you have last week, I think, starting from 7th. So आपको कुछ ऐसा डेट शीट, डू यू हैव एनीथिंग लाइक प्रैक्टिकल एग्जाम्स का कोई डेट शीट या कुछ यू हैव विद यू, और somebody has announced it to you?
नो सर, 9 से स्टार्ट होंगे प्रैक्टिकल एग्जाम्स।
ओके, 9th से शुरू होंगे, तो दैट मीन्स वी हैव 7th and 8th at least. Okay, so we'll start from Monday, or we'll see if, अगर कल हम इसको जल्दी खत्म कर लेंगे तो we'll start with the last unit of this, that is quantum mechanics. ठीक है? So it will not take more time because quantum mechanics में हम लोगों को सिर्फ we'll discuss what were the difficulties of classical physics, है ना, और उनको कैसे ओवरकम करता है क्वांटम मैकेनिक्स. विल डिस्कस व्हाट इज श्रोडिंगर्स इक्वेशन, व्हाट इज टाइम इंडिपेंडेंट श्रोडिंगर्स इक्वेशन, व्हाट इज टाइम डिपेंडेंट श्रोडिंगर्स इक्वेशन. And then finally, because particle in a box we discussed earlier also, quickly we'll go through that. If we have a particle which is inside a box, then it behaves like a wave or microscopic particle. Then to deal with this particle, to find energy levels of this particle, to study mechanics of this particle or dynamics of this particle, how we apply Schrodinger's equation, and then how we solve that Schrodinger's equation to gather more information about the particle. So this will be covering in the next lecture or next chapter. Okay.